So optimization is about finding the best outcome for a given set of information with possible constraints. So for example, you want to find the best or maximum revenue, or maybe you're trying to minimize the cost of manufacturing something, or maybe you're trying to minimize the time it takes for your fleet of mixer trucks with concrete to deliver their payload. All of these things about maximum and minimum can be addressed through optimization. Optimization is a very, very broad and important branch of mathematics. It also is what I did my master's in and my PhD in. I wrote algorithms for aerospace applications, and they were related, or basically the framework was optimization. There's different types of optimization. There's things that you can optimize. When I say optimize, I mean find the maximum or minimum for. There's different things that you can optimize. Some things are called discrete quantities. So when I say discrete, discrete refers to having something where there's only specific values that are possible. So for example, what is the optimal number of days that I should go to work? Well, people have studied this, right? And some people say it should be a 4-day work week or a 5-day work week. See, the optimal number of days of work is a discrete variable, because days, nobody's going to go to work for 4.36 days or for pi days. They're going to go for 1 day, 2 days, 0 days, 5 days, 10 days, whatever, if it's per month, for example. That's discrete. On the other side of the coin, there's continuous. Continuous variables are ones that are like you could have the in between. So, for example, what temperature should I set the refrigerator to in my food warehouse so that I minimize my electricity bills while maintaining a level of code for storing food? See, temperature is a continuous variable because you could have 29 Fahrenheit, you could have 31 Fahrenheit, but you could also have 28.692 Fahrenheit. So you could have these decimal numbers in between and virtually at an infinite amount of divisions in them. So what are we focusing on in this course? Well, discrete optimization is not going to be covered in this course. Like, we're not going to talk about those types of variables because the algorithms associated with them, although they're very cool, they're not really part of what I'm going to talk about, because you are just getting familiar with what a derivative is. And when we take derivatives, we usually refer to functions that are continuous, where the graphs are nice and smooth and they're not dots. Discrete graphs are usually represented by dots, or points. So we're going to talk about continuous optimization. Now, regarding optimization, there's a 4-step process here, and I have it right on the page here. So you really want to hone in your attention on these things here. It says here 4 steps, and the first step is to create or identify a function that is to be optimized, that is maximum or minimum. Then, once you have that function, then you want to take the derivative. So step 2 could be really easy, or it could be annoying if it's like a quotient rule or something, but it could be polynomial. That'd be really easy. So the derivative step is usually not too bad. And then finally here we have step 3, which is to take the derivative and set it equal to 0 and solve for x. Once you have these values of x here, those represent what are called critical values, and those values are associated with the best or worst possible scenario. Step 4 is how you verify that the value that you found for x it corresponds to the optimal or maximum or minimum, depending on the situation, value. So what am I looking for in terms of today's class? I'm going to be doing step 1, 2, 3, and then step 4 I'm not going to do. I'm not going to ask you to verify whether or not a solution that we find through this process is indeed a maximum or a minimum. Now you might be worried, you're like, this looks kind of scary. But the thing is that you've been doing optimization since grade 10. You remember those word problems in quadratics in grade 10 where you had to find there was like a farm and there's a length and a width and you had to find the maximum area or something? Those kind of questions? Well, those questions are optimization questions. It's just that those ones there you could get away with using a parabola and finding the vertex. So I thought that a nice question to start off with today as a gateway question is to do the same. Let's start off with a question for which the function is modeled by a parabola, because for that you are familiar with ways of solving it from high school. So let's take a look at this first question. So keep in mind there's 3 steps. The 3 steps that I'm going to cover. Create a function, or maybe you're given the function, find the derivative, and set it to 0. Tic-tac-toe, okay? So let's take a look here. I'm just going to write down that process here on the side in a just concise way here. So those are the 3 steps. Let's see if we can use them for this question. So it says here, the projection of cash flow for a project is given by this. Here's the function. Now, okay, fine, it's not the letter X here, but that shouldn't interfere with our process. You could have any variable there, and in the homework exercises that I gave you, I put variables other than T in there, other than X, sorry, in there. So for this question, the independent variable is time, or T, but you just treat it like an X. Anyway, the question's asking for the time when the maximum cash flow occurs. That's when. When is the time? And then how much? When and what? So they're asking for the T value and the Y value at the maximum. Part C here, has nothing to do with optimization. So that part C there is just kind of like a refresher on your quadratics. So let's talk about the process. Well, step 1 of the process is to identify or create a function. This is the most easy variation here because I am giving you the function. You don't have to create it. So step 1 here is a joke. Basically, I give you the function. So let's write down that function here. I'm just going to write it here. So we have y equals 70 plus 12t. Okay, so there's the function. That's step 1. I'll write that down here. I'll call it step 1. What's step 2? What do I do? In the chat, let me know in the chat. What's the next step? Yep, that's correct, Jai. Step 2, you find the derivative. So let's evaluate that derivative. What's y prime? What's the derivative of 70? What's this derivative here? Someone in the chat, let me know the derivative of this. That's correct, Praviti. I'm going to go through it for those that are not sure. The derivative of 70 is 0. It's constant. The derivative of 12t is 12 because it's linear. And then for this one here, you bring the 2 down, but there's already a 1.4, so you multiply 1.4 times 2, and you get 2.8. And you put t to the 1. But I'm not going to write the 1 there, so I'm just going to write t. Congratulations, that's step 2. What about step 3? What do I do with step 3? What do you do for step 3? That's correct. Let me know in the chat. I know I got 2 people here that are hitting home runs, and 3 people, sorry, in the chat hitting the home runs. But I want to let me know in the chat there that you get this. 12 minus 2.8 t equals 0. So then t is approximately 4.29. I'll take Praviti's answer. Thank you. So, what have we answered for this question right now? Are we able to answer part A or part B? What's the answer to part A? What's the answer to part A? Yeah, 4.29. The maximum cash flow. Okay, that's good. Now the question in part B says, what is the maximum cash flow? That's right. So what you do is you set t equals 4.29. If you do that, you get y equals 70 plus 12 times 4.29 minus 1.4 times 4.29 squared. I got well, you tell me what you got. What did you get? Did you get 95 point something? Is that right? 95 point something? Anybody got a number there? Thank you, Prabiti. 95.71. I'm going to leave it as 95.7. Thank you so much. Now, to answer the question fairly here, the question is that why is cash flow in thousands of dollars? So max cash flow is 95,700. That's to 3 sig figs. The question doesn't specify it, but as you know me well enough in the semester, if I don't tell you, I want 3 sig figs in the situation where you are forced to round it. So that's the optimization process, everybody. That's it. It's done. That's the answer. Now part C is something different, but it's not calculus. Part C is not calculus. I'm going to just discuss quickly here that how would you have done this in grade 10? In grade 10, you would have found the vertex. And the vertex would be 4.29, 4.29, comma, 95.7. You would have done that by whatever techniques you were taught, or you could use what I showed you back in September. And look at that, the vertex, these guys, these numbers here, well, they're the same numbers that you get. Like you're not doing anything new here in terms of like numbers. You're still getting the same answer you got in grade 10. See, you still get the same two numbers. So why the heck would I waste your time with this when you can just find the vertex? And the answer to that is very, very straightforward, because this function here is a parabola, and not every question in life is a parabola. So let's just get that out of the way. Not every question that you're going to get in life or that you can use to model a real life situation is going to be a parabola. This is why we need something more advanced like calculus. Now part C has nothing to do with calculus. Part C talks about when does the cash flow become negative. So part C is just a quadratics question and something that I would not ask you on a test, because I'm not asking you to find x-intercepts for parabola. But in this case, part C, just to finish the question, find the T-intercept. To be fair, it's called the T-intercept here because the independent variable is time, and that just means solve the quadratic equation. My typing skills have failed me today. Anyway, for this part here, guys, if you don't mind, I'm not going to actually like show you line by typing it. I just take a screenshot and just write it down, okay? Just to be fair to the process here, this is an optimization lesson, not a quadratic equation lesson. So I hope that you appreciate that. If anybody's watching this later on the recording, just pause it and try it yourself, please, and do what you got to do. But anyway, if you do that, you're going to see that the value is 12.6 years. So I hope that you don't mind that last thing that I did there, because like I said, this is not a quadratic equation lesson. So that's the first question there, and it was a parabola. So that's good. Nothing too dangerous. Let me know. What do you think? Let me know in the chat. What do you think about the process? What do you think about the process? Who's not taken calculus before? Who's never taken this stuff before? Let me know in the chat. Is this something that you can do? Oh, Siddharth, we're going to do 4 more. We're going to do 4 more. Yeah, I promise you, we'll do lots of them. So there's 3 steps here, and we're going to hammer out 4 more questions at least. And then with whatever remaining time we have, I'm going to show you something in Excel where I can show you how to code this in Excel, how to solve questions like this, it'll be pretty cool anyway, for those that are going to stick around during the breaks. Okay, yeah, let's hammer out a few more. Let's hammer out a few more. Number 2. This question is also quadratic. This question, you could also use a parabola and find the vertex. But we're going to use calculus because I want you to get used to the process. So let's take down our little algorithm here. Oops, I copied this thing. That was weird. So that's our little process here that we need to follow. As the sum and the length, the sum of the length and the width of a rectangular tabletop is 120. So let's draw a tabletop. I'm going to steal my picture. So I guess it's not stealing if it's my picture. I'm going to borrow it from the solutions that I wrote. So there's a picture, okay? We got a tabletop that's a rectangle, and it's like you see here, x by y. So what is the question asking? It wants the maximum area. So you see, when you see the word maximum in a question, or minimum, that is a red beacon for you to know that it's optimization. So we want the area to be maximized. Can someone tell me in the chat there, give me a formula for the area. What's the area equal to in terms of x and y? In basketball, we call this a layup. Yeah, thank you, Irvin. Now I'm going to use the letters in the picture, okay? But what you said is fine. So we have x times y. So there you go. The area is x times y. Now, step 2 is to find the derivative. Wait a second. How do you find the derivative? Sorry, I'm typing it and saying it. I'll just type it. So that's a bit of a mess, isn't it? Because there is a way to do it, but it's a much more advanced branch of mathematics, multivariable optimization. We're only doing optimization with one variable. So what we want to do is we want to go on the side here and identify a constraint. So there is a constraint in the question. So can someone tell me here, what is the constraint? Like x and y cannot roam freely and be whatever the numbers they want to be. What is the restriction on x and y? Read the first sentence out to yourself, and then write down an equation that would represent that constraint in the chat if you like. So it says here the sum of the length and the width is 120. So what is an equation that I need to write down that x and y must satisfy? Close, Prabiti. You did the perimeter. You did the perimeter, but this one just says the length and the width. Yes, just x plus y. I know it's a little bit counterintuitive. It obviously shows that you've done many questions in the past, because usually it'll be a perimeter constraint. But for this question, for whatever reason, it's a length constraint, of the length and width sum. So what we're going to do is we're going to take this constraint and rearrange it like that. And we're going to go back here and substitute in for y. And there you have it, my friends. Look at that. You have the area. You have the area as a function of x. Let me know in that chat, who remembers doing something like this in grade 10? Or maybe it was grade 11 for some people. Who remembers doing this kind of stuff? Let me know in the chat. Please let me know. Thank you, Irvin. Let me know. I want to see at least half the class respond, yes or no. It's been a while. Definitely been a while. I hear you there, man. Jai, thank you. Let me know. Some more people. Come on, let's go. But you failed this chat. Oh boy. Anthony, my friend, don't worry. I got lots of these questions. Lots of these questions. And we're gonna hammer out a bunch of them today. But they do become predictable, and I wish I knew you earlier, Anthony, because I would have hooked you up. Anybody else in the chat? Thank you, Anil. All right. Well, thank you for letting me know. Those who let me know. That's step 1. Everything that we did up to this point If I call this step 1, 2, 3, all of the stuff that we just did here, all of this insanity was step 1. That was all step 1. Man, the stylus is not working with me today. I give up. I don't know why it does that. Anyway, compare that to the previous question. How long was step 1 in this question? Well, it was just this. Step 1 was just this. Look at that. What a disaster, right? And then step 1 over here is like a marathon. So the point that I'm trying to say is that these 3 steps in the process, individually, they could be short or long. It just depends. So hopefully step 2 isn't too bad. Can you let me know? What do you think? Do you think step 2 is going to be easy or hard? You think step 2 is going to be easy or hard? It's so quiet. Yeah, it's going to be easy. It's just derivatives. Thank you, Anthony. Thank you, Irvin. And yes, Praviti, it's just derivatives. Yeah. So here's step 2. How did you know that you need to find the area first? Because the question says to find the area is a maximum. Okay? It says find the maximum area and find the values of x and y for the area. So no, actually, you just missed step 0. Step 0 is read the question. Sorry, that was a bad joke. That was a bad joke. I've done worse. I've done worse, Shaquille. Don't worry. I've done way worse. I'll tell you after this question. One of the funniest things I ever did. Uh, I'll tell you after. I'll hit the video off and I'll tell you. It's a really funny story. Anyway, what's the derivative here? What's the derivative of 120? X, sorry. What's the derivative of 120x? Thank you. And then the derivative of x squared is negative 2x. Thank you, Jai. Okay, that's step 2. And step 3 is to set it equal to 0. There it is. That's the answer. X is equal to 60. So now what you want to do, so I didn't highlight them in purple here, but you get the point. That's 2. Whoops. That's 2. Just to have the visual. So now we've completed our checklist. So now the question is, what do we do with this information? Well, we summarize. So what I usually do with questions involving geometry is I make a little table here at the end. And I'll do that just the way that I just said to you. So I'm going to make a table here and put down all of the dimensions. Whoops, it's just loading a table. So we have 3 variables. We have x, y, and area. And you can help me figure out what the values are. So the x value is 60. What are the units? 60 what? Thank you, Jai. And how do you get y? How am I going to get y? How would you find y here? Yeah, you said x to 60. So you go back here. Here's the formula for y. And you go back here and you make x equal 60. So you would have here 120 minus 60 is 60 centimeters. So that's good. And how would you find the area? Well, with the area, you have 3 formulas. You could use any of these and you get the answer. So for this case, you could just multiply x and y, or you could plug in x directly into the second or third version. It doesn't matter which permutation of the equation you use, because they'll all produce the same number. So I'll use x times y, because area literally is x times y. So that's 60, whoops, that's a 60. 60 times 60, which equals 3600 centimeters squared. And there you have it, my friends. There's an optimization question, another one that you would have done back in the day in grade 10 or grade 11 maybe, and you would have had a good old time doing those. So just bear with me for a second. I'm gonna just I'm gonna go to one of my I have a folder with my own notes of this kind of stuff from back in the day. So I'm just gonna dip into my grade 10 notes and see if I can find some min-max questions, because it's kind of nice if you get to see some more. I'll share them with you if I do locate them, but the thing is that they all have the same pattern. Create a formula. If the formula has more than one variable, like here it has x and y, if it has more than one variable, then you are forced, at least for this category of questions, to use what's called a constraint. A constraint is just something on the side that you have to guarantee that you are within the parameters of the question. So anyway, there's a couple questions. I'd like to do one more question with you, and then I'll offer you a break. And then after the break, we'll do a couple more. Now, I just to give you the insight onto the chapter here, this is not really a chapter. It's just basically one section of the textbook. Your final test, so for max it's 60, yeah. And I'm not asking you to prove to me that it's a maximum. So yeah, I can just say that here. I'll answer part A in here. No, max, yeah. So the answer to part A is that the dimensions are. I'm really sorry, my computer's lagging today for some reason. I've been holding off to do the software update until the semester ends because I don't want anything to screw up on my computer until I finish marking your final tests. So anyway, there's the answer to that question. I was going to say that this booklet is 8 questions, and our goal is to cover 5 of them. The remaining 3 are pretty tough, but they're also not going to be on your final test. So the questions that I show you, questions 1 to 5, your final test will have 2 questions. One will be easy and one will be a bit tougher. And by easy, I mean of the same, this question that I refer to here and the previous one, I would say are on the easier side because they are things that you have set up before in high school. If it's a parabola, I consider it to be an easy question. With all due respect, it is a question that you should have solved in grade 10. If you didn't have a good time back then, this is the time that you can redeem yourself. And also, if you had a tough time setting up these kinds of questions and you want to see more examples of these, you can send me an email and I will locate some of the notes from back in the day that I made and I can share them with you. But I don't want to saturate the Blackboard data that I have, all those notes that I give you, and dump a file with like 20 of these questions, and then you think that overly represents what's on the exam. So, question 3, and then we'll do a little break. Who's taking advanced functions? Drop me a hello in the chat there. Who's taking advanced functions? Hello, Irvin. So I got 4 people out of 27. That's pretty low. Yeah. Okay. Let me add to that question. For those that have said hello, bonjour. Who has seen this picture before? Who's seen a picture like this before in math class? Because right now I got about a third of you. Yeah. Whoever hasn't responded yet, let me know. Have you seen this picture before in math class? Nah, no. Okay, that's fine. I'm just saying that for those that did advanced functions or equivalent, especially in the Ontario curriculum, you would have seen this kind of question somewhere in the textbook. So basically what's happening is you have a piece of paper, or in this case it's cardboard, so it's a little bit more durable, and you're going to cut out the corners. So you're going to see these corners here? You're going to cut them out with scissors. And when you do that, what are you going to do? You're going to fold it and make a box out of it. So I'm going to try my best to draw this without the computer crashing. So what you're going to do is see these purple lines here? You're going to fold along the purple lines. Can you imagine folding them? If you fold them like that, then this thing here that I'm shading, it represents the bottom or the base of a box. And then Okay, I'm having a tough time with the stylus here. I'll get around it by doing something a little bit different there. So when you fold it out like that, you're going to get a box. Can you imagine that box? Do you see that box in your mind? I'll leave it over there. Okay, so now the challenging part is you need to tell me the dimensions of this box. I haven't read the question yet. Don't worry about this stuff here. Just ignore the stuff at the bottom. I want you to tell me the dimensions of the box. Can you tell me how tall the box is? How tall is the box in terms of the variable x? Yeah, it's x. That's x. And this length here is 16 from here to here. The diagram's not to scale. You'll have to let that one go. I'm sorry about that. I think I recycled this diagram from one of my other notes. But yeah, this is a square. Anyway, we'll let that one slide for now. So can someone tell me what is this length here? What's that length right there? And what I'll do is I'll highlight it on this diagram. I'm asking you what this length is because it's the same number. For BD, you are correct. Yeah, that there is 16 minus 2x. Very good work. So that's 16 minus 2x. And just maybe in a different color, let's use orange here. That length is also going to be 16 minus 2x because it's a square and I didn't really draw it well, but I hope that you will forgive me or I am forever in your debt. Well, not really forever. Maybe for the next hour. There you go, okay? So those are the dimensions of the box. So that's all the drawing you're going to get from me for this question. 55% quiz boost. That sounds like we're playing a video game. Quiz boost. I like that. Oh my goodness. Anyway, you guys are funny. Okay, so what are we trying to do here? What the heck? What is the maximum possible volume? Oh, okay. You want to find the volume, but you want to find the maximum of the volume. So there's your optimization question. Let's get that step one there, okay? Step one. The volume of the box, we want to create a formula. So what is the volume of the box here? Well, what's the volume of a box? In the chat, what's the volume of a rectangular prism? Thank you. That Jai, you're killing me here, buddy. You're like 5 steps ahead. You're the chess master. Yeah, that's right. You wanna plug in the length, width, and the height. Before I plug them in, let me just write a little step here first. Okay, length is 16 minus 2x. Width is 16 minus 2x. Let's just summarize them. Whoops, get rid of that. And the height is x. So that, yeah, Jai, that's perfect. Thank you so much. So we're going to plug in those quantities into the equation. And when you do that, you get, I know that the x at the end looks really funny, but it's literally to the formula, right? So anyway, I'm going to ask you to expand this out. And when you expand it out, you're going to get 4x squared. Just a second, I'm going to check against my notes. But then you have to multiply by x. So I'll do it in 2 steps to be fair. Okay, so there's the equation for the volume of the box. Are there any questions about that formula? How do you feel? Do you feel okay setting this one up? It's a little bit gross. Thank you, Mohammed. So basically, if you can set up the formula for this question, that's the hardest part of the question, is setting up the formula. Because if we go back to the algorithm, the 3 steps that I want you to do are to create a function or identify it, find the derivative, and set the derivative equal to 0. So this question here the step 1 is really, really annoying. And that's why this question would be considered a harder question, because you have to create the function, and it's a little bit of a pain. So let's do step 2 and step 3, and then that pretty much wraps up the question. Step 2 is the step 2 we know is to take the derivative. So I'm just going to take the derivative here. So v prime equals, help me out in the chat here. What's v prime? Anybody? Thank you, Irvin. Yeah, 12x squared minus 128, right? I think it's 128 plus 256. Thank you. Yeah, I figured it was a keyboard thingy. You're just fine, my friend. Look, for some reason, I'm having a hell of a time trying to type on my keyboard today. And there's a lag too for some reason. I'm pretty sure that I need to do the software update soon. Anyway, let's take this and set it to 0, which is the next step. So just because, yeah, possible. Let's take this and set it equal to 0. This is not a quadratics lesson, and you are still, I don't know. You guys can sort it out yourselves. You need a better security system, Irvin. Keyboard security. So set this equal to 0 and solve using the quadratic equation. Now, or you could factor it. So I think for this one, I actually factored it. So I'm just going to tell you the answers to these. If you don't mind, everybody, I'm not going to write down the method here. I'm just going to tell you the answers. You're going to get x equals 8, or x equals 8 over 3. So those are the two answers that you'll obtain. And for those that are a little bit rattled about how to get to there, I don't mind just tossing in some of the algebra. I'll just toss some of the algebra here on the side, but I'm not going to make it a centerpiece of today's discussion. So if you go back later and you want to watch the recording of this, you'll see here I wrote down the equation here, and then I divided out by 4, and then I factored it, and then I got those things. That's great news, Siddharth. I'm really glad. I'm really glad. So I want to talk about what answers here are admissible. So it's okay. Put the checklist on the side. Absolutely. Absolutely, Praviti. Can't go anywhere without a checklist. Are you kidding me? I should have put it. I've been trying to be very diligent about this kind of thing. Let me just squeeze that quadratic stuff here. I'll put the checklist right here, okay? You know what? It gives me the opportunity to highlight. And you know me with my highlighters. So identify the function. Look at Johnny here. Johnny's got the highlighter out now. Now you know it's serious. When your professor pulls out the highlighter, either he's really bored or he's overly excited. Okay, I'm the latter right now. So anyway, step 3, there you go, okay? Anyway, which one of these answers should we throw away? We gotta throw one of these away. It's inadmissible. Which one? Okay, you want to throw away 8 over 3? Why you gotta be so mean? Because it's a fraction? You're being mean to it because it's a fraction, aren't you? Don't be mean. Don't be hating the fractions. You gotta throw this one away. Because look at the original dimensions. I want you to put 8 here. What happens if you put 8? What do you get for length? You get 0. Can you have a box with 0? Do you think 0 is a maximum area? The maximum area is 0? That makes no sense, right? So 8's garbage. Don't use it. 8 over 3 is going to be the answer. I'm not going to ask you to justify why 8 over 3 is the answer, but I do expect you to know that you should reject the 8, because the 8 is no good. Produces a 0 volume. So that definitely is not a maximum. So because of that, you can go back to this equation here, length, width, and height. And I'm going to insert it here quickly. And you can put 8 over 3 in for x. If you don't want to use fractions here, that's fine. You could use decimals, but I'm going to stick to 8 over 3 because I don't have a need for making it a decimal right now. So if you do that, then the length is going to be equal to 32 over 3, or approximately 10.7 inches. The width is also going to be 32 over 3, or approximately, and you guessed it, 10.7 inches. And finally 8 over 3, which is approximately 2.67 inches. And also, don't forget our volume, maximum volume. Just a second, everybody. I gotta fix that. I dragged the background image. And the maximum volume, you just multiply those together. So Vmax equals LWH. I'll have you substitute that on your own. It's not too bad. And you're going to get roughly 303 cubic inches. There you have it, my friends. Done. See you later. We did 3 solid optimization questions. Why don't you take a nice break now, and we'll do 2 more questions after the break. And then maybe I'll show you, if there's some time before the quiz, I'll show you with Excel how to do this in Excel. If there's no time for me to show you in Excel today, if we want to focus on doing the questions, what I'll do is I'll make a separate little video, like I've done them before on my channel anyway, and I'll put a little video, like a 2-minute video, on how you can take a question like this and solve it using technology. I think it's very valuable for you to see. And because you're students at the college, you get Microsoft Office as part of your tuition, I think, right? Correct me if I'm wrong. I think that all employees and students get Office. Am I wrong? No, yeah, I'm pretty sure that's right. Yeah, thank you, Jordan. I'm 99% sure that was right. Because if you have an ID, thank you, Jordan. If you have an ID, you get it. That's right. Sorry. Anyway, take a break. 10:15, okay? 10:15. 10:15. Go get yourself a coffee like me, and enjoy a little bit of the beautiful morning outside. Yes, Jason, we have a quiz today. The power nap. The quiz is open at. I made the quiz open at 11, but I only made it open at 11 but I still want to be teaching a little bit into the 11 o'clock hour though. But I know some people want to write the quiz at 11. Thanks, Jason. All right, guys, I'll be back in 13 minutes. So we have a rectangular prism-shaped building, and we're given some information about the building, and then there are associated costs with constructing this building. The question is, when you really dig down through the words here, we know that this is an optimization question because we want to minimize the cost of constructing. So we therefore need to create a question, or a formula, sorry, that represents the cost of the building. So in order to get a cost of the building, we need to figure out or assign variables to the information. So what I'm going to do here is I'm going to just label the diagram as you see it on the side here, length, width, and height. But let's take a look here. The length here of the base is x, and the width is y. The height, though, is a little bit interesting. The height is actually going to be 6. Like, you have no choice for the height. Can you see that? That's probably like not an obvious thing there. Whoops. So I'll justify for you why the height is 6. So let me just put a height here of 8 temporarily, and then we'll talk about why it's 6. So based on the question, we're given some information. We're told that the volume is 6,000 meters cubed. We're also told that the base area is 1,000 meters squared. So because of those two things, that immediately forces us to have a height of 6. Because remember, volume is the area of the base times the height. So you might be wondering, why is it so weird? Why didn't I just tell you the height was 6? Well, the reason is that when you look at information in terms of practical applications, sometimes the information is redundant, and sometimes the information is really convoluted or all scrambled together. So it's like this in practical situation. You want to make a building. So then you go, okay, I want to make a building. I'm going to make it for like a storage facility, which is what this one is. So I know that the client wants me to have a volume of 6,000 cubic meters. Think of like that TV show Storage Wars, where they have those storage units, and maybe that each storage unit is, let's say, 10 cubic meters if it's one of those small ones. Then you want to have 600 units. So now you know that the customer wants 6,000 cubic meters of volume. But then you go to the city and you're like, I want to build one of these things. And for whatever reason, they say, oh, building code says that you cannot have more than 1,000 square meters of area on the base. Or in other words, building, whatever that is in square feet, if you multiply by roughly 10, the building cannot be covering more than 10,000 square feet. That, for whatever reason, there's a code for that, okay? So then you see that certain things kind of force you so that you can't optimize the height of the building. The height has to be 6. So that's what I'm trying to say there with that opening information. So this is 6. Too bad, so sad. You can't change it. It's going to be 6. But on the design front, that's good because then there's less confusion about what you should do. So now our objective is to figure out X and Y so that we minimize the cost of the building. Well, the building is made of different facets or planes. You got the foundation and the base, you have the walls and the surrounding building structure, and you have the roof. So what I've done here in a very simplistic way is I've assigned a dollar value per square meter for those regions of the building, those surfaces of the envelope. So let's take a look here. Okay, well, let's talk about the cost of the foundation. So what's the cost of the foundation? What's the cost of the foundation? Anybody? It's $400 per square meter. Let's put that down. $400 per square meter. And then the cost of the walls, and by walls I mean the walls, the brick, or whatever the external is, the whole thing. That facet of the building is going to be 200. And then the roof. What about the roof? How much money per square meter? 300. That's good. Okay, so we're kind of getting somewhere. We've laid out the information. It's a little bit annoying, but it's there. We also know one more thing. We know that x times y equals what? What does x times y equal? Yeah, it equals the area. That's our constraint. The constraint is that x times y equals it's only one time though. Oh, the foundation. Oh, I see what you're saying. Sorry. That's the roof. Thank you, Anthony. That's my bad. That's my bad. Sorry about that. We're okay again? That's my apologies on that one. Okay, so the constraint here is based back on what Prabhiti said. Prabhiti said that that's an area. We know that x times y is 1,000 because it's told to us in the question. We know that x times y is 1,000. That's a constraint that we cannot avoid. So for that reason, we could manipulate this equation. Remember that question we did with the tabletop? It's the same kind of idea, but the constraint's phrased a little bit differently this time. We're going to use a constraint in the question. So that's what we're working with in terms of the given information of the question. So now it's time to build our cost function. So we need to create a formula that represents the cost of a building. So the cost formula, the cost equals, so it's going to be the foundation and the floor. So the foundation and the floor is 1,000 square meters. I'll break it into pieces, okay? Cost of something. We'll put here base. Cost of the roof. And then cost of the walls. The cost of the base, there is actually no optimization occurring there. The base is 1,000 square meters times, and the base we said was $400 per square meter. So basically, too bad, it's $400,000. And the same thing with the roof. The roof, there is no play. The roof is going to be 1,000 square meters, and the roof costs $300 per square meter. So no choice. That's $300,000. So I didn't make the question too difficult with the numbers in the sense that the roof and the base are not flexible. You have no choice. It's going to cost you $700,000. The only thing that you can play around with is X and Y. So for the walls here, there's 4 walls, and each wall has a different area. So for example, you see the one that I'm kind of tracing out with my cursor here? What's the area of that rectangle in terms of those values there, X, Y, and 6? What is that rectangle area? Can someone let me know in the chat? Yeah, it's 6Y. Thank you, Irvin. Okay, and wait a second. How many of those walls are there? There should be 2 of them. So it's 6Y and 6Y, and then you also have this one here, the front one if you want, that one there, the longer one. So what's the area of this rectangle that I'm tracing out? What's that area? Thank you. And there's 2 of those. And all of those walls together are going to be worth, or cost, I should say, $200. So if we clean that up, that's going to be a little bit annoying. It will be. Prabidi, it will be soon. I promise you. I'm not ready yet for that, but you are right. If we clean this up, we get 200 times 12y plus 12x. You can't help it. You're good. You skipped a step because you're ahead of the game there. That's good. I'm just going to clean that up a little bit. So this is 2400 y plus 2400 x. But the thing here is that when you put this all together, the cost equals, if you add these all together, you're going to get 400,000 plus 300,000 plus this stuff. And it's not looking very promising here because you have too many variables. You have too many variables. So Prabidi mentioned in the chat something that was interesting. I'm just going to organize this for, actually, I don't need to organize it. 700,000 plus 2400 y plus 2400x. Sorry, I was just checking something on my computer there. Yeah, see this thing here? Too many variables. Too many variables. What can we do? Well, you see what Prabidi wrote in the chat there? There's a fraction over x. What Prabidi did was she took the y there, and I'll just color it in red, and replace the y with this. Because this way, just like that tabletop question earlier, now you'll only have one variable. one independent variable. So then you'll have here 700,000 plus 2,400, 1,000 over x plus 2,400x. And now you're cooking. Now you are moving it along. Okay, so this equals let me see here, 2,400 with 3 more zeros, so that's 2.4 million, x to the negative 1. All right, my dear friends, what the heck is happening here, right? You just got absolutely hammered with formulas. And you know what the sad thing is? If we talk about the algorithm, how many steps have we completed of the process? How many steps have we completed? 1. Isn't that the most demoralizing thing ever? You spent the entire question pretty much just, look at it. We spent, I've counted it, 14 minutes doing this, setting it up. That's step 1. But don't worry, there's hope. There's hope now. Because step 2 and step 3 aren't that bad. So let's do step 2 and 3, okay? I'll say steps 2 and 3. So we take the derivative. The derivative, I'm not going to tiptoe around this one. You bring the negative 1 down, so that's negative, and then a bunch of zeros, and then x to the negative 2. That is a 2, plus 2,400. That's step 2. And then step 3. So we take that and set it equal to 0. So we have 0. 0 equals this stuff. And at this point, it's just semantics with the algebra. Hopefully nothing too dangerous. So if we cross multiply, or we can do a switcheroo here, actually. I'll do a switcheroo. You've seen this before with me in the fall. We're still in the fall, but you've seen it before, like in October somewhere, maybe. Anyway, what do you get there? What does x squared equal? I get 1,000. It only makes sense to carry the positive solution here, so I'll just write the positive solution. So there you have it. So the question's asking for the dimensions, and that's it. What are the dimensions? So here's the last part of the question. We're almost done now. So the dimensions are length, width, height. So the length is going to equal x. The width is going to equal y, which is 1,000 over x. And the height is 6. Because the height, we had no choice. We had no choice for that height. Too bad. Although having no choice in a mathematics question is nice, because then you're not going to screw it up, hopefully. So x is 31.6 meters. The width here is 1,000 divided by 31.6. It's going to be the same number because it's a square. It's going to be a square base. Now, not every question is going to be a square, and the base is going to be a square, but in these two cases, it is. Anyway, what I'm highlighting here in green is the final answer. So there you go. So why would I give you this question when it ended up being a square? Isn't that boring? It's so boring. Oh my God, why would I bore you with the squares? So what I want you to do, just as an exercise on your own, is imagine though that the walls here they didn't cost the same. Imagine that the front wall and the side wall didn't cost the same. Where would you have a situation in real life where that's true? Well, perhaps I can open up I'm going to open up a browser window and just show you a picture of something that would motivate you for why you would want to do that. So if I don't find it within 10 seconds, I'm going to give up. Okay, so the image that I'm looking for is something in retail. You know, buildings that are retail buildings, they have a certain behavior. That's funny. Um, so like retail buildings, like usually one side of it's glass or mostly glass. And why do they do that? Well, because they're trying to advertise, right? So you wonder why the building like a car dealership. The example I want to think of is a car dealership. When you look at a car dealership, what does a car dealership building look like? Like the most traditional ones, they're going to be long buildings like that, very long buildings. And then this side on the front here is typically made of glass, mostly. And glass is cheaper to put up than a masonry. So that's why you'll see the building long and slender, because they'll get the same area that they need for a cheaper price because the one side is mostly glass. So that's why the shape is like that. So you could simulate that here. If you wanted to imagine a situation like that, you could take this $200 per square meter for the walls, and you could split it into two types of walls. Wall for the front, and then walls for the backs and the side. So maybe the front wall is cheaper than the back and the sides. And if you were to experiment with that type of costing, it would obviously change this expression here, because maybe the $200 wouldn't apply to all four of these walls, but only three of them. And you would multiply the fourth wall by a different number. And then that way you could actually see that the optimal shape is not a square for the base. So I promised you 5 questions. We did 4 of them. So we're going to do example 5 now. And then after example 5, there are 3 extra questions, which I will post the solutions on Blackboard. I can say with certainty, questions 6, 7, and 8, you don't have to worry about them for the final. So don't worry about 6, 7, 8, okay? You only need to understand the ones that I'm showing you here, and if I were to give you an exam question, I would try to keep them in the same level or quality of question as the ones I'm showing you. So this last one here is a pretty tough question, and not something that I would put on a test without having shown it in lecture. It's pretty gross, but let's see if we can make sense of it. I should mention this question is very practical. So we have 2 factories that are 8 kilometers apart. And imagine like a highway between them. And you want to think about where in between those 2 factories that are emitting pollution, where you would want to be situated to have the minimum exposure to pollution. So let's see that on a diagram, okay? So here's a long road. I'll try to do this diagram without it crashing. There we go. So this is 8 kilometers. And over here is factory A. And here's factory B. So factory A looks like that. And it's got some pollution. And then factory B emits 8 times as many pollutants as factory A. So factory B will make it nice and big. It's 8 times as much pollution. Okay, there it is. I'm not going to draw 8 of these streams, but you can imagine that, right? So they're 8 kilometers separated between them. Imagine that you wanted to put a development like for residential, and you wanted to put in, this is a highway, so you're not going to go off the highway way into the middle of nowhere to put the development. You want to keep it near the highway. So do you put the development halfway? Do you start building houses halfway right here? Do you build them halfway? What do you think? Would it make sense to put houses halfway? No. Okay, so Jai, would you want to put the houses toward the left or toward the right? Yeah, toward the left, because this factory is more pollution emitting than the one at A. So the question is, where do I put it? So I'm going to say it like this. What is this distance? So to make the question a little bit easier, yeah, it is like a seesaw. It actually can be solved like that too, but there is a bit of more complication there. So what I'm going to do is I'm going to put an axis here. So I'm going to put a just a origin here, and then I'll do this, okay? So that's my x-axis. And then what we need to do is figure out what the total amount of pollution is for each factory. So if I go here and I plot, I can create a function for the pollution of the factory A and the factory B, and I can see what the total pollution is as a function of x. So you can see here that the formula is given right here. The pollution concentration or amount as a function of x is given by k over x squared, because it's an inverse proportionality. As you saw earlier in the semester, we had inversely proportional to distance squared. I wouldn't explicitly ask you to create this formula because I would just give it to you like I have given it here. So anyway, this is actually the formula for the pollution of factory A. This one here, the pollution of factory A, I'll just type it. So the pollution emitted by factory A is P of A as a function of x, which is equal to k over x squared. Now, we need to figure out what the pollution emitted by factory B is. So in this case, the pollution emitted by factory B involves two things: the distance squared and also the factor of pollution. Since factory B is 8 times as polluting as factory A, then its constant here will be 8k. It's 8 times the pollution. But we still need the distance. So that's where we go back to the diagram to figure that distance out. So I'm going to move that development over here. So that's where we want to be. I'm going to call this distance x. That's why this formula is x squared, because A is a distance of x away from here. But this distance is whatever B is. B is this far away from A. Can someone tell me what this distance is in terms of x? How far is factory B from here? That's correct, Prabiti. It's 8 minus x. Very good. Because remember, this distance here is x. The total distance is 8. So you do 8 minus x. And that's the value here for the distance to factory B. Sorry, from factory B to that development. So it's 8 minus x squared. And these two functions together represent, collectively represent the concentration of pollutant that you could get as you're sitting somewhere x distance away from A. So we can say that the total pollution at x is going to be the P of x, which is P due to A, plus P due to B. And if we do that here, that formula becomes the following. That's going to be k over x squared plus 8k over 8 minus x squared. And that, my friends, is step 1. That's all step 1. I want to give you a visual for this because it is a little bit weird, and I understand that you probably are getting a little bit scared. So what I'm going to do is I'll plot this in Desmos to show you what it looks like. So just give me about 10 seconds as I open up Desmos. So here's Desmos. Now I'm going to use a value of k equals 1. So here's P, there's the first one, PA of x. I wonder if it allows me to do subscripts. Okay, it does allow me that. That's good. So PA of x was k over x squared. So I'm going to use k equals 1, if that's okay. Because you could do that as well. So what you can imagine here is that there's a factory where it is right here, and then it's the pollution is decaying like that. I can go here in Desmos as well and say x is greater than or equal to 0, because that's what makes sense. See, if you're near 0, then the factory is giving you a lot of pollution, but then it decays quickly. Obviously, it's just a model, so you would have infinite pollution at the factory, but you wouldn't want to be at the smokestack, living at the smokestack. So let's take this one here and just copy it and create the pollution for factory B. Over here, it's 8 times as polluting, but the distance on the denominator is going to be 8 minus x squared. So you see factory B there, and I'm just going to go x is less than or equal to 8. And I should just go here, actually make it like this. Let me make it from 0, 8. That makes more sense. And I'll do the same thing with factory B. So there's a graph of the two factories' pollution. And remember that 8 is over here, so the second factory is here, and the first factory is here. And here's halfway. Here's 4, which is halfway. And as Jai mentioned correctly, the minimum is somewhere over here. It's not where they cross, though. In order to find the minimum, you want to add these together. So if I take PA, and I go y equals, which is what I'm doing right now. So if I do P of x equals that, plus the other one, that's the green graph. That's the graph that we're trying to optimize, everybody. Is the green one. I'm going to click on the answer. So the final answer is right there. The answer is 2.667. So let's take that, and I'll steal it and put it in the actual document, just like that. It's not the intersection between the blue and the green, just because of the features of the graph. It's because the sum, it's their sum. You're minimizing their sum. You're not finding where they hit each other. You're finding where their sum is a minimum. And where their sum is a minimum is not necessarily where they cross each other. Okay? They will be different answers. Yeah. You're adding two graphs that have nothing to do with each other under normal circumstances. And it's just weird. Anyway, let's get that answer. So the answer is 2.667. Let's see if we can get that answer. Okay, so now the objective is for you to do step 2, which is to take the derivative of this and set it to 0. So this is our objective right here. This is what we're trying to maximize or minimize. In this case, we're minimizing. So let's hit a step 2 on this. To prepare for step 2, it would make sense to rewrite the function like this. And this question is a derivative question that is within what we covered last week. So let's talk about the derivative of each of the terms separately. So the derivative of this. Now, keep in mind, k is a constant. So it's like pi. So if you bring the negative 2 down, you're going to get negative 2k. And then you'll get x to the negative 3. That takes care of the first one. Now the second one's a bit more irritating because it involves power of a function rule. It involves power of a function rule. So just to remind you here, if you had y equals, do you remember this from last week, hopefully, because your quiz is on it, then y prime equals n f of x to the n minus 1. So that's the rule that I'm talking about. Let me give it some flavor here, a little spicy flavor maybe. So we're going to do this one now using that rule. Remember, k is a constant. So if you bring the negative 2 down, you're going to multiply the negative 2 by the negative 8k and get negative 16k. Just got to make that red so I'm fair to the the labeling here. And then you'll have here 8 minus x to the negative 3. So it just looks just like the rule that I'm presenting over here. But then you need to take the derivative of whatever's in the brackets. And in the brackets, we have 8 minus x. The derivative of 8 minus x is negative 1. So after the dust is settled here, we have p prime of x equals, let's clean this up here and write it with positive exponents. That's negative 2k over x cubed. If you're getting a little bit tired or like kind of rattled, we're almost done the question. Like literally right now we're just doing a bit of algebra and we're done. So we'll get here plus 16k over 8 minus x cubed. And now you said, that was step 2 by the way. That was all step 2. So we set this equal to 0. And you'll see that we're in the home stretch now. It's plus 16k because you have a minus 1 here. Minus 1 times minus 16. It's all good. All good. Thank you for asking, because I know that someone else is asking it as well in their mind, but they're just maybe shy to ask it out loud. I just gotta fix the slide for a second. Something went a little bit weird. Weird there. Weird. Let's figure that out. Okay. Okay, there we go. For some reason, my math menu is not cooperating. Okay, so hopefully you got a nice understanding of what happened there with the derivative steps. So now time to finish this. We're almost done, people. So we're going to move that 2k over x squared over, or x cubed, sorry, over. Put an equal sign here. Cross out the k's because they're not 0. Okay? And I would cross out the 2 as well, but you can do that after here. So you end up with this, cross multiply. So we have 16x cubed equals 2 bracket 8 minus x. I'll continue the solution over here. You can divide the 16 and the 2 by 2. So if you do that, you get 8. That. And the neat thing about this is that you can take the cube root of both sides. So you get 2x equals 8 minus x, 3x equals 8, x equals 8 over 3, which is approximately 2.67 kilometers. And there you have it. That's the answer. See it? 2.67. 2 and 2/3. That is the end of that question. So how's everybody doing? Yes, Prabiti, tell me what part of the question. Okay, yeah, I could definitely do that. So I'll come back to that answer at the bottom there shortly. So the idea here is that you are given a relationship that describes the behavior of pollution as you go away from a source. That is an inverse proportional to the square relationship. So what that means is that factory A is going to have this diminishing type amount of pollution, and so will factory B. But because factory A and factory B are polluting at different amounts, in other words, factory B is 8 times as much, you need to set up the relationship for the pollution for each of the factories separately, and then add them together to get a total contribution of how much the pollution is. So if you add up their individual contributions, then you get the graph here, which is green. And if you like, what I can do is I'll highlight that in green there, and then I'll just point to the graph and say that this graph here in green is when k equals 1. You can even let k equal 1 to solve this question, because it doesn't matter the value of k. All that matters is the relative amount. So now that you have a combined pollution for both factories, now the objective is to find the minimum amount of pollution. In other words, what value of x along this axis would give you the least amount of pollution? To do that, we know that we would have a derivative because it's an optimization question. So what we do here is take the derivative of this. Now, finding the derivative of that requires a little bit of preliminary work as per our conversations last week and the week before. So what you want to do is rewrite the function like this, because now it looks like the rules that you're familiar with. The one in green is just the power rule, so you bring the -2 down, and then you make the exponent -3. And for the one in red, you have to use the more advanced power of a function rule over here on the right. And then you bring the -2 down, but then you bring the exponent to -3, and you put the derivative of whatever's in the brackets, which in this case is -1. At that point, the rest of the question, you simplify the derivative, that's fine, but the rest of the question is just solving this equation. So all of the writing that I'm doing here from where I've highlighted here until the very end is about solving this equation. So that is just algebra. That's not calculus anymore. So, and the way that I did it is not the only way you can do it. There's lots of ways, but ultimately it does become an equation that is linear, which is very cute. And you get the answer, which is 8/3, and it corresponds with the prediction that we have from our graph using Desmos. So hopefully that was a nice walkthrough, but not the math stuff so much that you were saying. Is that better? So the equation of P is always given. Are you talking about this one here at the beginning? Yeah. So this question definitely relates to physics, and no one's asking you to know what the relationship is for something like that. 100%. I would never give you a question on a test from physics where I'm like, oh, you should know the formula. The only formulas that you should know coming into a final test regarding this chapter, which is optimization, you should know the area of a rectangle, the area of a triangle, the area or the volume of a box, a rectangular box, basic stuff, okay? Like you don't have, and nothing too much to stress out about. Oh, you're very welcome. That's the least I could do. You've been such a very, very good contributor to the class today, and always. So, yeah, that's enough of that. It's 11 o'clock. The quizzes are available, but you don't have to write the quiz right away. If you want to stick around with me a little bit, I can show you how to write the optimization in Excel. I can show you actually how to code an optimization in Excel, and it won't take me more than 5 minutes. So if you want to stick around for that, I welcome you to do that. I think it would be a worthwhile experience. All of the stuff that I've done with you today, though, is recorded, and I will clean it up, cut out all the gaps and put it on YouTube. Hopefully, I will do it by Friday, because Friday is my last lecture. And that's about it. So let's set up that optimization question. So if you want to stick around for that, feel free. If you want to take a break, do something else, feel free. So I'm just opening up an Excel workbook. I think you guys will enjoy this. So there's Excel. Actually, I need to keep it open so you can see the options. So we have X, Y, and then area. And I'll say here the constraint. So these are just labels. These are all labels, okay? So I'm just going to put a value for x and y. They're going to be wrong. It says that it has to add up to 120. So I'm going to do this, guys. I'm going to put 110 and 10. Obviously, 110 and 10 are wrong. They're wrong. But the question is, you want to get the maximum area. So area equals x times y. So you see up top here, I have area equals x times y, like that. And this is my constraint, the sum. So this equals x plus y. So that's our constraint, and this is our objective. Let me put that over here. This is our constraint. This is our objective. If you go under some tools here, there's something called solver. You see solver over here? So you hit solver. So I'll put the solver here. And now it's going to open up this window, hopefully, in this decade. Oh, it's on my other tab. Let me bring it up here. There it is. So it looks a little scary, but let's go through it. It says set the objective. So the objective, I'm going to click, and I'm going to click on this because our objective is that. It's to get B4. We want B4 as our objective. And it says by changing the variable cells. So what are the variables that we want to play with? So we're going to click on these guys because we want to play with these variables. Are there any constraints? Absolutely. We want to add a constraint that this number here, so I got to scroll up, you haven't seen it there. We want to say that this cell here equals 120. And just add it. Remember, the answer was 60 and 60. When I run solve, look what you get. Do you see it? And I'm just going to, it says here, do you want to keep it or do you want to do something else? You can restore if you don't like what the answer is, or you can just say, okay. So that's the answer. Now take a look here. You're going to be like, hey, buddy, look, it's 60, but that's not 60. Well, to computers, up to so many decimals, it is close enough to 60. But if you really just want to be a bit more like secure with yourself here, you can just change the formatting of the cell to 3 decimals or whatever you feel like. And there you go. Okay, so that's a very quick way, a very quick example of optimization in Excel. I haven't used Excel for that in probably a year. And you see, it didn't take me too long to do it, and it won't take you long either. But you can set up some really incredibly complicated optimizations there. And if you ever use this stuff in the future and you want some like guidance on it, feel free to hit me up and ask questions.